Good morning, good morning, good morning, my dear RNA warriors, NEET warriors. Your ROAR NEET aspirant series is about to take a new turn because we are almost nearing the end, and that is going to lead us to a new beginning. So today we are going to do the waves on a string and sound waves. And in this particular topic, you will see what a wave is, wave on a string, or in general a wave, sound waves and different kinds of classifications, how to describe a wave equation, what are the different terms you might have seen in different 12th standard chapters as well. And then we are also going to go towards wave speed for string, sound, and the intensity, power, energy of a wave, right? This is what we're going to do in today's lecture. Remember, interference, beats, and standing waves, I'll be taking it up as a separate part because that in itself is a huge topic, okay? So today we'll do till that, and I hope you guys are all ready for it. Hi Krishna, good morning, all the warrior Pandus. Hi evening star Pala. Yep, all those students who are new to the channel, make sure your voice is heard so that I get to know you, or else, yeah, I would never know you by name. Yep, hi Disha, nice to see you back. Hi Vivek, good morning. I'm not really sure, Krishna, my health is going on and off. It had gone off, but again, since Saturday, again it has picked up the fever. So after this class, I'll be visiting a doctor. Whatever your future profession is, that is what I'm going to do. Yeah, I'll be visiting a doctor immediately after this class. I'm just waiting for the clinic to open up. Yep. Hi Vivek. Good evening. Good morning. You are new to the channel. Welcome. Join in. So if you have not yet marked your attendance, please like the video right now because YouTube also understands you are interested in NEET then, or else it will show you some distracting videos. And subscribe to the channel, or else you will miss out all the important updates, notifications, academic content. All right. So let's start with what is a wave, and I have a beautiful introduction over here. A lot of calculations and graphing calculations and all that I will be showing you, and graphs also. So a lot of simulations as well. Cool. Let's start. What is a wave? See, when you hear the word wave, you think about sea waves, right? Or you take a string and on that string there is a nice wavy nature or sound. All these are waves, yes. But what exactly is a wave? Let's understand it by a simple demonstration. Okay, I hope you can see there is a tap. This is basically a pond of water, or this is the top view. And if I turn on this tap, water will drip and it will fall on this pond. See, it fell, and do you see something went? Something went? Yes, something went. What is that something? The disturbance. Disturbance means basically there was a tide, something like a tide, some bulge was there in the water, and that ripple or that bulge of that water went, everywhere. This is the medium. This is the source. A source created a disturbance. The disturbance began to propagate. When I say the disturbance began to propagate, that means the energy which was there in the drop now was carried by the medium in all the directions. So a phenomena where a disturbance in a medium or disturbance in general by a source creates energy to be transferred, that phenomena is called as wave. Without any particle going from here to here. Please understand the water was intact. It's not like the water went from here to here. It's the disturbance, the energy which starts to flow. That is basically a wave. I hope you are able to visualize. And this is also true for any other kind of wave as well. Let's say, for example, I take sound. Okay, what we hear, this is a speaker. There is air over here. The sound travels in air, water, solids everywhere. So if I turn on the speaker, some disturbance is created. You saw that diaphragm, moved back and forth. It created some disturbance. That energy moves in all the directions, and if it falls on my eardrum begins to vibrate, and that's how I'm able to sense the sound. Correct. So that is how sound wave will propagate. Same way, you even have light. You turn on a torch and turn it off. it has created a disturbance, and the disturbance of light, which is electromagnetic wave, travels in all the directions. That's a separate chapter of 12th standard. If you notice, we have done it in the last week or something. Yes, so light wave travels in all the directions, so the energy is being carried forward. Are you now able to understand, guys? Everybody with me? Clear till this point? Yes? Cool. So let's write down what a wave exactly is. Okay. A wave is nothing but you have a source. That source basically creates disturbance, and that particular disturbance will travel, that will basically travel or basically propagate the energy. And all of this happens with a condition: no particles move to the destination, from the source. They might move at their own places, like the ripples of the water. When they go, the water particles might just go up and down like this, but they are not going from the source to the destination. When I talk, the sound particles, the air particles will go, here and there, but they are not going from me to wherever the person is listening to that sound. So that is what is very important. So they travel, they propagate energy, and without having the particles go from the source till the destination. That is basically a wave. So examples of that is basically obviously sound, the pulse on a string. You take a string and you move it up and down. So pulse on a string. Not just that, even ripples on water, which I just showed you. You drop a stone or drop a drop of water, those disturbances go across that water surface, ripple on water surface. Not just that, even earthquake, even an earthquake is nothing but a wave. Yes, even for that matter, light is a electromagnetic wave. So there are so many more examples, guys, of waves, okay, which we are going to see. Yep. All right. Harish, I'll be taking it up as a separate lecture, maybe by the weekend or by next week for sure, okay? Because superposition, interference, everything has to be taught together. It's a nice big unit and it requires full concentration. So that's the reason why I'll be taking it up separately. Correct. Awesome. Cool. Awesome. Now, there are different ways in which you can classify the waves. You can classify the waves into different categories in different manner. One of the manners in which you can classify the waves is whether it requires medium or it does not require medium. So one is called as a mechanical wave, and then you have non-mechanical wave. Mechanical wave, basically, they will need medium. They need medium to travel. They need medium. Here, there is no need of medium. There is no need of any medium. Example of this is sound or earthquake. Without the earth, the ground, obviously the wave won't travel, right? Without the air, the sound won't travel, right? So in space, on moon, you cannot talk to each other because there is no air to carry that sound energy. So it needs medium. Whereas electromagnetic waves from the sun, light, how does the light come from the sun without any medium, right? So it does not need medium. Even if a medium is there, it's okay. It can pass through air, water, glass, so many transparent things. So light, electromagnetic waves are basically non-mechanical waves. I hope this is absolutely clear. Then you can also classify the waves as something called as transverse and also longitudinal. Yes, longitudinal, transverse as well as longitudinal waves. Now transverse means what? The energy will be going in a peculiar direction. The energy will be going in a direction. Let's say the energy is going in this particular direction. In transverse means perpendicular. So you will see that the particles will be moving like this, perpendicular to the direction in which the energy goes. So the motion of the particles is basically perpendicular to the direction in which the energy goes. In longitudinal waves, the motion of the particles is parallel to the direction in which the energy goes. The examples of this, many examples are there. For longitudinal waves, you take a long spring, and imagine you compress it suddenly. That compression will go through the spring. The particles will go back and forth, and as the energy goes, the particles' motion is along the direction. So that would be basically a longitudinal wave that is called as a kink in the spring. Not just that, even sound wave is nothing but a longitudinal wave. But you take a string and you generate a pulse. That pulse goes up and down, the energy is going like this, so that motion of the particles is perpendicular to the direction of the travel. So basically the pulse on a string is definitely a transverse wave. Even electromagnetic wave is a transverse wave. Electromagnetic wave is basically a transverse wave. Everybody fine till this point? So these are the basic classifications that you must know: mechanical, non-mechanical, transverse wave, longitudinal wave. That will be there in your syllabus. All right. Cool. Next, let's go define some basic properties of a wave and who creates what. Okay. So starting off with, say for example, when you talk about a wave on a string, when you have a wave on a string versus a sound wave, usually these two chapters generally it's better to learn together, wave on a string and sound wave. That's why I put the title also accordingly. Imagine the wave on the string looks like this, and sound wave, it will look slightly different. You'll see why, because they are something like this. Okay, so here what you see is basically, just look at this. This is called as the crest. This is wave on a string. Imagine this was the string, you make it go up and down. There will be crest and there will be a valley which is called as a trough. Crest, trough alternatively. Here you will have compression compression, and then this part is basically called as rarefaction. Rarefaction. Alternate compression, rarefaction. Meaning the air is compressed, then after that it is like a vacuum, it is rarefied, then dense, less dense, so alternatively. And this will keep on propagating. That's the difference between, this is a sound wave which is longitudinal, this is a wave on a string which is transverse in nature. And I can show both of them to you, no issues. Say for example, so we just saw waves introduction in a bit, all right. So let's say we go back over here. Yes, let's have a look at this, and let me also open physics. Meanwhile, waves. Now look at this. Look at this, guys. This is a string. Okay, this is a string basically, and I just make this hammer go up and down. Can you see? There is a pulse which is going, and if I make it go up and down, let's make it go up and down in slow motion. See, you can see all the particles are going up, down, up, down, up, down. So this is a transverse wave. See, take that green particle. It is not going forward, but it feels like something is going. No, the energy is going towards the right hand side, but the particles are moving like this. So this is a transverse wave. You can check any of the particles, like for any reference, this green particle has been marked so that you can see it clearly. Any green particle you see, so that you can see clearly. Where is it? It is always there. So that is how this is nothing but a transverse wave on a string. Similarly, I can show you longitudinal wave also. Yes, see this? This is, I told you, right? Take a long spring and suddenly compress it. That thing is called as a kink. This is like a kink. Okay, you take a long spring, you press it and leave it. You can see the compression is going slowly. Notice my hand. Notice my hand. See how the compression is going slowly. Even you can see rarefaction. Rarefaction is also going slowly. Compression, rarefaction. So this was a longitudinal wave. This is a transverse wave. This is like a transverse wave, up and down. I hope this is absolutely clear. Cool? Yep, amazing, right? All right. Now, different more terminologies over here. This one over here, A, and here you have something called as PM. This A is basically called as the maximum displacement of the particles, which is called as just the amplitude of the wave. It is expressed in centimeters, meters, millimeters, up to you. Here, there is no graph like thing, but there is variation in the pressures. If the pressure normally around us is 1 bar, let's say the pressure goes to 1.2, then becomes 1, then becomes 0.8, 1, 1.2, 1, 0.8. Can you guess what is the maximum variation in the pressure? This is basically max variation in the pressure, max variation in the pressure, because this is sound wave, longitudinal wave. Think about it. From 1 it became 1.2, then came back to 1, then came back to 0.8, then 1. It is like your simple harmonic oscillations. What's the variation? Yes, it is basically 0.2. So the variations of pressure, what's the maximum variation? That is what PM stands for. It is also called as the pressure amplitude. What is it called? It is called as a pressure amplitude of that sound. Pressure amplitude of that particular sound wave. Keep that in mind. Okay, so this is the amplitude of the wave on the string. That was the pressure amplitude of the sound. Okay, great. Next, if you go from one crest to the next crest, or from one trough to the next trough, or from one identical point to the next identical point, from one identical point to the next similar looking identical point the first time, that is your lambda. So lambda happens to be nothing but your wavelength. That is nothing but your wavelength. Obviously, it is expressed in meters, centimeters, millimeters, kilometers, up to you. And you define a new number called as k, which is nothing but 2 pi divided by lambda. Now you can see the numerator is nothing but in radian. The denominator is in meter, so radian per meter. This is called as angular wave number. What is it called? Angular wave number. This is called angular wave number. Keep this in mind. I hope this is absolutely clear. Okay, so this is angular wave number 2 pi by lambda. Just 1 by lambda is just called wave number. You have seen just wave number in which chapter? I wouldn't have taught you that. Yes, you would have learned that from Diksha ma'am in chemistry in atomic structure. 1 by lambda. Lambda is wavelength. 1 by lambda is wave number. 2 pi by lambda is angular wave number. Got it? So that's an easy way to remember things. Right? Angular wave number, wavelength. How quickly you make it go up and down, tuck, 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 very fast, coolly, or very casually you are doing it. So very less frequent. This is very frequent. So that is basically how frequently you are doing it. That means the frequency. Correct. So let's talk about the frequency, my dear students. So frequency. F is nothing but 1 by t, where t stands for the time period of oscillation, where time period of oscillation is basically the frequency. Time period of those oscillating particles, these particles going back and forth, these particles going up and down. Look at this, how frequently they are going. If you measure the time, maybe they go up and down in 0.5 seconds. Maybe it goes back and forth in 0.5 seconds. Then the frequency will be 2 hertz. So 2 times in a second. That's your frequency. Obviously, it is expressed in hertz. Just like lambda frequency, angular wave number has an identical similar term that is basically called omega, which is nothing but 2 pi divided by t, which is the same as writing 2 pi into f. This on the top is a radian, as you can see. Bottom you have seconds, so radian per second. So this is basically called angular frequency. Just like this was angular wave number, so this is frequency but angle wise. So angular frequency, just like we did it in our SHM. Angular frequency, radian per second. Is this absolutely clear? Very good. Awesome. So wavelength, crest to crest, trough to trough, or similar points. Then how much is the maximum variation of the pressure or the displacement? That is amplitude or pressure amplitude. Then angular wave number is 2 pi by lambda. Angular frequency is 2 pi by time period. 1 by time period is also the frequency of that particular wave. Now, are these also related to each other? Yes, you will see that right over maybe here or here. We can go. Say for example, we go to this thing and let's say I'm dropping water at regular intervals of time. So you will see trough, blue, crest, black, trough, example. So, my dear students, you can see the distance between one blue to the next blue is the wavelength. One black to the next black is the wavelength. And the wave is propagating in all the directions. How frequently the water is falling decides that frequency. Let's say I increase the frequency. You can see that I have increased the frequency. Now what do you see? The wavelength has become smaller. The gap distance between two blacks or two blues has become smaller. If I make it less frequent, slowly you will see the gap between one black to the next black will suddenly increase. Correct. So if I increase the frequency, the wavelength will reduce. You can see now slowly the wavelength has reduced. Now I will reduce it even further. By dropping it more frequently, you will see the gap between two crests, gap between two compressions will reduce. Correct. So they are inversely related, but what is the relationship? So well, that depends on how fast they are traveling. So basically the speed of the wave, how fast is this wave traveling ahead, that is called as the wave speed, correct? So wave speed. So the wave speed v is nothing but this particular frequency that you have, into the wavelength, that is one way of doing it. Or if you don't like it like that, or also you can do it one more way. Instead of frequency, you can put omega by 2 pi. Instead of frequency, you can put omega by 2 pi. And instead of lambda, you can put 2 pi by k. You will notice you will get this as omega divided by k. Omega divided by k. It's one and the same thing. Just if you don't believe me, do one thing. Instead of omega, put 2 pi by 2 pi into f. Omega, you put 2 pi f. Instead of k, you put 2 pi by lambda. 2 pi cancels, lambda goes on the top, multiplies with frequency. It's one and the same thing. So both these formulas give you the wave speed. So I think we should block all the important stuff over here, like this one, obviously important. This one, obviously important. Wave speed is frequency into wavelength. If wavelength goes up, frequency comes down. If frequency goes up, wavelength comes down. This is angular wave number definition. This is your angular frequencies definition. All right. So all these things very, very important. Correct. I hope this is absolutely clear. Now you might be wondering, sir, if frequency increases, will speed increase or decrease? Sir, if lambda increases, will speed increase or decrease? Will frequency change? Sir, I always get confused, sir. No worries. Shreyas Sir will teach you. Who decides the wavelength? Who decides the frequency? Who decides the speed? All three have different criteria. Let's understand that. As you can see, the frequency is under my control. And who is deciding that? How frequently it falls? This guy is called as the source. Same thing happens with even sound or even light for that matter. Say for example, I take a speaker. How will the frequency of that sound emitted be decided? By the speaker. And what is a speaker? A source, a torch which emits light, a candle which emits lights. It is a source of energy. It is a source. So the source decides the frequency. How fast it is traveling, how fast that sound is traveling, how fast the light is traveling, how fast the wave on the string is going depends on the medium. And we know that light travels at different speeds in different medium. We also know sound travels at different speeds in different medium. In fact, every time it's the external parameters which decides how fast the sound, the light or the wave will travel. So I'm going to give you a beautiful flow chart which will help you remove all these problems. So talking about speed, the wave speed is basically decided from two things. One is called as the inertial and elastic properties basically of the medium. Inertial and elastic properties of the medium. These two together decide something called as the wave speed. Inertial and elastic. Now what is this inertial and elastic? I'll come to it. But there are some properties of the medium. Basically medium decides the wave speed. Keep that in mind. Next, who decides the frequency? Who decides the frequency? The frequency, like I said before also, is always decided by our source. Our source decides the frequency. As an effect of both of these, the wave speed and the frequency, the final outcome of them is the wavelength. The wavelength is decided. Pavam guy, he's like the Pavam guy, he's decided in the end Like when you are traveling anywhere for a picnic or somewhere out, maybe you are going in a car or a bike, what happens? First the elders will sit wherever they have to sit. You are chiller pillar, okay, you adjust here, you sit on my lap, oh no space, where to put you, okay, you sit in the dicky. Happens, no? All the chiller party, all the chotu puttu people, what happens? All the kids, finally they will be decided in the end. So wavelength is that pavam fellow. That pavam fellow gets decided in the end. Wave speed will be like, I will be decided by, oh, you are air, okay, I will travel at this speed. Okay, you are water, I will travel at this speed. In glass, I will travel at this speed. Oh, in stone, I will travel at this speed. Frequency, okay, who is creating me? Okay, is that speaker? Okay, that torch. Okay, that candle. Okay, that some person is making that string go up and down. The source will decide that. In the end, the wavelength will be decided. Okay, so that's how the logic goes. Yeah, correct. So this is the actual flowchart which you should obviously remember. So wave speed decided by the medium, frequency decided by the source, wavelength is V by F. Done, dusted. All right. Cool. Now that we understand till here, okay, what is wavelength, what is frequency, what is angular wave number, what is angular frequency, what is amplitude, and what is crest, what is trough, what is compression, what is rarefaction. Okay, sir, can you tell me how will the wave equation look like? What is the manner in which you describe a wave? Fine, you can tell that this is a wave having this much amplitude, etc. Is there a wave equation? The answer for that is also yes. We'll come to that, but before that, let's start solving some basic questions so that you get some idea. All right, here is the question. If a wave on a string has a time period of oscillation equals to 0.2 seconds and the wave travels at 40 meters per second, find number 1 frequency, number 2 omega, number 3 wavelength, number 4 angular wave number. These are the questions. Come on, let's try to do this. Welcome everyone. Hi Joe, hi Rathiz, Sukanya, all right. Hello Beula. Come on, think about this. Time period of oscillation is given, so from that frequency can be easily found, which is 1 by time period, which is 1 by 0.2, which is just going to be 5 hertz. So that's the frequency. Next, omega, that's 2 pi f. So that will be 2 pi into 5. 5 2s are 10. So 10 pi radians per second is basically your omega. That is also done. Okay. Next, we have to find wavelength. Wave speed is frequency into wavelength. Wave speed is given to be 40. Frequency is 5. Wavelength we can find from this. So lambda will be 40 by 5, which is basically 8 meters. So wavelength also done. Last thing is k. K is nothing but 2 pi divided by lambda. So 2 pi divided by 8. So it will be nothing but pi by 4 radian per meter. Pi by 4 radians per meter. That is the answer for k also. So this is how you get it. Correct. 5 hertz, 10 pi, 8 meters. Very good, Sukanya. Perfecto. Awesomeness. Moving on. Now, here is the next question. If the medium through which sound travels changes such that the speed becomes 1/4, then the wavelength will become dash, the frequency will become dash in the new medium. What do you think should come in spite of that, instead of that? Fill in the blanks. Come on, think about it. Come on, let's see. If the medium through which the sound travels will change, then imagine what will happen. Well, if the medium changes, this medium decides what? I have told you this. Medium decides the speed. The speed will change. And that's what has happened. But the source, the person, the thing which emitted that wave was still the same. It's the same energy which is going from that original source. It's just changing the medium. The original source was the same. So there is no reason for the frequency to change. So the frequency will remain the same. It will remain basically the same. And the reason for that is because the source is still the same. Medium has changed. That's okay. Now think about it like this. V is equal to F lambda. Wave speed has become 1/4. Frequency is basically the same. So hence what should happen to the wavelength? LHS becomes 1/4. RHS also should become 1/4. So hence the wavelength will become 1/4 of the older wavelength. Correct. So frequency will be same and the wavelength will become 1/4. If it was 16, it will become 4. If it was 4, it will become 1 meter. So this is how logically you can solve this question. Very good. Now there are 3 modes of heat transfer. You might have an idea, you would have learnt it at basic school level. Even if you have not learnt the thermal properties and heat transfer of 11th standard physics, still you know this. So the question is out of conduction, convection and radiation. These are the 3 modes of heat transfer. Conduction, convection, radiation modes of heat transfer. And when I say heat transfer, that means basically it's nothing but energy transfer, energy propagation. And whenever energy propagates, what happens? It's a wave, right? So maybe it's a wave, I don't know. So out of them, which ones are basically waves? Question mark. Which one is basically a mechanical or a non-mechanical wave? Mechanical or non-mechanical wave. Which one is a mechanical or a non-mechanical wave? Which one of them are just waves? That is the question. Come on, think about it. Very, very interesting question, my dear students. Out of the 3 modes of heat transfer, conduction is when, okay, you are holding a rod, one end is on the stove, the heat energy goes through the rod and into your hand, the other end also becomes hot. Convection, the part of some surrounding becomes hot or cold, the wind will blow from one place to the other and the other place also will become hot or cold. Next, radiation. The sun emits radiation and that's how it reaches us. Or maybe you have a lamp somewhere. The heat reaches you not because there is something directly connecting you, but invisible rays are there which makes that energy reach you. So obviously out of them, now you understand which ones are waves, which ones are not. Conduction and radiation are waves whereas convection is not a wave. Reason why convection is not a wave, because the particles carry and move towards the destination. And remember, that was one of the main criteria for a wave. The particles should not start from the source and then we'll be like, okay, come here, take. No, they should not do that. They should stay wherever they are. They can move, but in their own place. Like teacher will tell you, right? Listen, you cannot leave your bench. On the bench, you can move here or there, you can lift your hands, whatever. But you cannot leave your bench. You cannot leave the classroom. So that's the way you should think of a wave. Whereas conduction and radiation, yes, the particles stay as it is and the energy propagates in both the cases. Energy propagates. But in case of a conduction, you need a rod, you need a solid, you need some object for those particles to carry that energy. That means it is basically a mechanical wave. It's a mechanical wave, correct. Whereas radiation is in the form of electromagnetic. Radiation means light, X-rays, gamma rays, infrared, ultraviolet, yellow, blue color. These are radiations. So this is nothing but electromagnetic waves. And electromagnetic waves are always non-mechanical. They are always non-mechanical because they don't need medium. So the light radiation from the sun reaches us even when there is empty space, vacuum between the earth and the sun. Cool. Awesome. Cool. So we have done quite a few questions on the introductory part of the waves, wave speed, and also the flow chart as well. So now let's come to the wave equation which I was just talking about. So let's talk about the wave equation. Now what is the meaning of a wave equation? I'll tell you. See, imagine this is x-axis, and for now let's take this x-axis as the direction of wave motion. This is the direction of the wave propagation. Sometimes this is also called as the ray of the wave. Like light rays, what does light ray indicate? The direction in which the light is moving, the direction in which the light energy is going. Sometimes it is also called as the ray of the wave. Okay. Say for example, I call that line as the x-axis. You can take it y, z, r, whatever you want, doesn't matter. We can take the example of a transverse wave for now, and maybe our wave is something like this right now. After some time, this is at t is equal to 0, or let's say t is equal to t1. After some time at t is equal to t2, the same wave would have gone somewhere else, maybe. So after some more time, maybe like this. As you can see, the wave is slowly moving ahead. It is slowly going ahead. Let's focus our attention on any one particle, any random particle, doesn't really matter. Okay, say for example, a particle here. Let's see what is that particle doing even. Let's see what is that particle doing. That particle was here, then it is here, then it is here. My goodness, it has definitely changed positions. First it was here, then it is here, then that same particle is here. Don't you see that if I call now this particular direction, this particular direction as our y-axis, example, can you see that the position of that particle is changing with time t1, t2, t3, etc.? Yes, definitely it is changing. t1, t2, this was t3 supposedly. Yeah, t1, t2, t3. It is changing with time. So definitely, if you ask me, the particle's y coordinate, definitely is a function of time for sure, is definitely a function of which time are you looking at that particle. So definitely time comes into play. Not just that, which particle am I talking about also matters. If I'm looking at some other particle only, that will have different y values. If I'm looking at some particle over here, you can see at different instances, it has different positions. This guy is here, this guy is here, this guy is here now. The value of x only is different. So definitely it also depends on the value of x. So any wave equation will depend on two variables. You tell me when are you looking and where are you looking. So x is basically which particle are you talking about, and where is it. This tells me when am I looking at it. So then I will get to know where is my particle exactly. So this is x is basically which particle are we talking about along the x-axis. When am I talking about? I will tell you where it is along the y-axis. This is a wave equation. Is this absolutely clear, everyone? Cool? Perfect. Awesome. Sir, what is this f, sir? Will this be like log, exponent, some quadratic, some cubic, some root? What is this f, sir? This f decides the shape of the wave. Yes, it decides the shape of the wave. This looks, imagine, you might have seen heartbeat looks something like this, right? How that shape of that wave is, or whether it is just like this, or whether it is just like this. So the shape of the wave, how it is, that is decided by this particular function. I hope this is absolutely clear. Cool, everyone? Okay. So now that we understand it, let's play around with it as well. Let me just get it over here. Okay, let's stop and let's get to our graphing calculator and let us make a wave equation and see how can I make it as a function of time and x and see the wave over here. All right. So starting off with y, yes, is equal to some function. All right. So let's do one thing. Let's take some function like x multiplied by t. Okay, x multiplied by t, and I square it and add a slider for time. This has to repeat. Okay, and not just that. This will start from, let's say, 0 to, let's say, 10, and at a step of 0.1, enter. Okay. Okay. Now look at this. Some random thing I've written, x into time, and see what happens. I'll just start playing it. Right now you can see the solid red line. Okay, is the graph. I will change it. Oh my God, it became like this. Just observe it once more. As time increases, it became like this. Is this a wave? No, it doesn't look like a wave. It is just becoming like this. What is this? This is not a wave. Wave has to move, no? Wave has to move. So this is not a wave. Oh, it is not a wave. Let me make it x, let's say minus t or something. Okay, x minus t, it is looking some function like this. Let me play this and see. Oh, this looks like something which is moving. This looks like something which is moving. Yes. Now this looks like a wave. Okay, sir. Sir, what if I make t square over here? Then will it look like a wave? Let's see. No, I mean, it went somewhere and all. Let me just zoom out so that you can see. It is slow. It is accelerating like crazy after that. So not a wave going at a constant speed for sure. What if I make, forget this square and all that. Okay, just like this, instead of x minus t, let's make it x plus t and see what happens now. Oops. X plus t, observe what is it doing. Oh, it is going towards the left side, guys. It's going towards the left side. It's going towards the left side, x plus t. But if I make it x minus t, then it is going towards the right hand side. Can you see that? It is going towards the right hand side. Oh, interesting. Sir, I have now more ideas, sir. Okay, tell me what is your idea. See, what if instead of this equation, let's say I make it y is equal to some other equation only, let's take. Let's say, 2 divided by something like 2x, or let's say 4x plus 6, and then t, where is t? T, and yes, okay, and maybe I make it raised to 4 or something. All right, let's see what is this going to look like. Oh my god, it's gone up like crazy. Maybe I'll add some number over here, 2 plus, okay. Now it looks like something. Okay, we are seeing something. Guys, can you see some nice bump over here? Can you see some nice pimple over here? Let's see what happens if I play this. Oh, it is going somewhere. Wow, so cool. So cool, guys. Just look at that bump over here once more. It is going somewhere. Wow, it is like a wave. It's going towards the left hand side. Let me make that plus as a minus. And let's see now what happens. It is going towards the right side. So one thing you are seeing, whenever I put a minus sign here between x and time, it is going towards the right or positive side. Whenever I put a plus, then it is going towards the left or basically the negative side. It's basically like opposite. Wanna come, S. Abhishek? Amazing, right? So all these are like wave equations. I changed the function. See how the wave equation only changed. Let's go to another wave maybe. Y is equal to, let's take some other wave. Maybe sine and maybe x and then plus and then t and then okay, this is some equation out here. This is some equation out here. Let me see what will happen if I play this. Oh, it is going slowly towards the left hand side. Can you see that? Because I put a plus. Instead of plus, if I put a minus, wow, it starts going towards the right hand side. So all these are wave equations. And what if instead of x I put it as 4x? Oh, it is still looking like a wave. What if instead of time I put it as, let's say, 3t? Oh, it is still looking like a wave. What if I put some number outside like 5? Oh, it is still looking like a wave. Okay, so all these are wave equations. From this, what is the general idea that you get? That function can't be any random function. It will be something x, something time, plus or minus. Something x, something time, plus or minus. This can be minus also. This can be plus also. Doesn't matter. Even if it is plus, doesn't matter. It will be going towards the left hand side. Is that right, everyone? Okay, perfect. So our wave function how should it be? In general, any wave's function which looks like this, y is equal to some function. What is that function going to be? That will be always something x, and that something x is basically actually k into x, and something time, that something time is always omega t over here, and you can have plus also, you can have minus also. So you can have plus, you can have minus. So this is how the equation should look like. If it is minus, it's traveling, the wave moves along positive direction of the x-axis. And if it is a plus sign, then the wave moves along the negative direction of the x-axis. That something x, something time, that somethings are k and omega basically. So this is your general wave equation, which is absolutely very, very important, of course. This is the in general wave equation. Okay, keep this in mind. Now, I'll give you some examples and you will quickly be able to figure out whether it's a wave equation or not, and what's the wavelength and what is the wave speed, etc. Everything will be able to figure out. Let's just have a look at some examples. You have to tell me in all these examples, is it a wave equation? Next, if it is a wave equation, what is the value of k and what is the value of omega and what is the value of the wave speed? This is what you have to tell me in all these examples. This is the first example. The first example is like this. Y is equal to 3, 2x minus 5t raised to 4. Number 2, y is equal to 2x plus 5t raised to 4. Number 3, y is equal to x minus 2 upon t plus 2. Number 4, y is equal to x square t cube. Number 5, y is equal to 5 by 3x plus 4t whole square. Number 6, y is equal to 3 sine 4x minus 8t. These are your examples. Come on, think about it. Meanwhile, I'll just drink water and come. Some things are very obvious which are not wave equations. Like this one, this is x, this is t raised to 4, 100% this is not. Even this x is there on the top, time is there below, this is not. This x time multiplied with each other, it is not. Something x, something time plus or minus, and then whatever you want to do. Something x something time, and then whatever you do. Something x something time, and then you do whatever you want. Yes, these are basically wave equations. So whatever multiplies with x, becomes your k. Whatever multiplies with x. So whatever multiplies with x becomes your k. Whatever multiplies with x becomes your k. Whatever multiplies with time becomes your omega. Whatever multiplies with time becomes your omega. Whatever multiplies with time becomes your omega. Okay. So what is the wave speed? Wave speed formula is omega divided by k, correct? Omega divided by k. So here wave speed will be omega by k. So 5 by 2. So this will be 5 by 2. Here to nothing, this is also nothing. Here the wave speed will be 4 by 3. 4 by 3. Here the wave speed will be 8 divided by 4, which is basically 2. Is that right? So these are the wave speeds. Next, which direction are they traveling? Because it's minus, it's along the positive direction of x. Here to nothing, this is also nothing. Here this is positive, so this is negative direction of the x-axis. Here this is minus, so this is traveling at a speed of 2 meters per second along the negative direction of the x-axis. So this is the direction, the speed, and some of them are not even waves. So now did you understand what is wave equation and what is not a wave equation, and how to judge the parameters inside the wave? Now the best part about this chapter, and in your NEET syllabus, you mainly study 99.99%. Only these questions will come. Chumma, I gave you this just so that you have an idea, but other than that, you just need to know the sine, cos waves. Other than that, you don't get anything else. So basically, you get something called as the sinusoidal wave equation. In a sinusoidal wave equation, what happens is, it's a beautiful wave like a sine wave. So this is, let's say, your x-axis. This is your y-axis. Your wave might be going like this. Okay. This might be the amplitude. From here to here might be the wavelength. Okay. So the wave equation looks something like this. Y is equal to a sine. You can have kx plus or minus omega t, or a sine omega t plus or minus kx, or even you can write it as cos kx plus or minus omega t. It doesn't matter whether you put cos or sine, and then you can also put a cos omega t plus or minus kx. It doesn't matter which term comes first. It's not necessary always x should come first, then time, doesn't matter. And one thing you should know though, you can have an additional term like we had in SHM, and that additional term over here, that phi is basically like your phase constant, which tells you what you are doing initially, the initial condition of the wave. So this phi is basically called as your phase constant, and this phase constant tells me the initial condition of the wave, initial condition of that wave, whether the wave was starting from here, here. Where was the wave? What was it doing initially? Omega, I have already told. K, I have already told. A is basically the amplitude. A stands for obviously the amplitude over here. A is basically your amplitude. Rest of the terms have the same meaning as before. Rest of the terms have the same meaning as before. That means your basically K is nothing but 2 pi divided by lambda again, and your omega is nothing but 2 pi into f, and your wave speed, the speed with which your wave travels, is nothing but omega by k, which is also f into lambda. Same things as before. So all these things is, or you can use sine or cos, really doesn't matter. Just like in SHM also, sine or cos doesn't matter. Okay, I hope this is absolutely clear. Correct, very good. Now, in such a sinusoidal wave equation, because the wave shape looks like a sine function, the shape of the wave, which is like a bumpy road, is a sine function. Every particle in it performs simple harmonic motion, like the one over here. Here, see, the particles are performing simple harmonic motion. The particles are performing simple harmonic motion, SHM, up, down, up, down, up, down. So therefore, the particles perform a simple harmonic motion. Very important. The particles will perform a simple harmonic motion. And because these particles will go up and down like this, all the particles, they will have the same amplitude. Even the frequency will be the same. But there is one thing which will not be the same. Even though this particle here, they have the same frequency, they have the same amplitude, one thing which will not be the same is they will not be going up and down together. That means they will not be in the same situation. All these particles are not in the same situation. When this particle has already completed up and down motion, this particle does up and down motion later on, the situation is different. It's like this is a 10th standard kid, 9th standard, 8th standard, 7th standard, 6th, 5th. So this guy will first give the board exam. Then after that, after 1 year, this guy will come to the next standard. So there is a delay. There is a situation difference. They are in different states. They are in different phases of life. So that's why they will have phase difference. So they have the same amplitude and frequency, but different situations. Different situations meaning different phases. Situation or phases. They have different situations or basically phases. If you see that any one wave can be associated with one revolution, one rotation, one cycle. So think of it like this. Any one such wave, one particular wave is basically one oscillation, or it is like a one cycle. And when you complete a cycle, one round, what happens? You complete 360 degrees or basically 2 pi radians. And one wave is nothing but one wavelength. So a wavelength is a 2 pi radian. A wavelength has a phase difference of 2 pi radian, meaning, say for example, over here this is the crest, and somewhere let's say this is like the wavelength. So these two particles go up and down together. It feels like they are together, but actually there is a cycle difference. That means if you go behind, you will see every particle is lagging by some amount. And if you come back exactly one cycle, 2 pi radians behind, you get a wavelength. So a wavelength is 2 pi radians worth of phase difference. So if a wavelength is 2 pi radians worth of phase difference, what's the phase difference between this particle and this and this, this and this, this and this, any two particles separated by some small amount? What's the difference in their situations or their phases? The answer to that is given by, so therefore the phase difference the phase difference delta phi, the phase difference, which is basically your delta phi, is given by, see, you have 2 pi radians of phase difference for separation of lambda, 2 pi radians for lambda. So for x difference, let's say there is a particle here, let's say there is a particle here, and let's say there is a particle here. So the difference between them distance wise is delta x. So for a difference of delta x, what's their phase difference? So for 2 pi radians, you get 2 pi radians worth of phase difference for lambda. So for delta x distance, how much is the phase difference? Radian per meter into meters, meter cancel, radian will be remaining. This is the formula. Phase difference between 2 particles separated by some amount. Phase difference between 2 particles separated by some amount. Phase difference between 2 particles separated by some amount. Some amount, there is some difference in the phase. Is this now absolutely clear, my dear warriors? Yep, very good. Okay, last thing, just like I said over here, all the particles perform SHM with the same frequency amplitude. So what is the maximum speed of the particles? Maximum speed of the particles, think about it. Maximum speed, VP, velocity of the particles max, what will that be? Just like SHM, A omega, correct? Similarly, maximum acceleration of the particles, maximum acceleration of the particles, acceleration of the particle, maximum, just like SHM, A omega square, correct? Right? So all these things you have learned in SHM, same things you can use it over here. Same things you can use it over here. So this is sinusoidal wave on a string. On a string. Similarly, you can write a wave equation sinusoidal equation of sound wave, of basically sound wave. Now, what do I mean by sinusoidal wave equation of sound? Observe it carefully. Okay, so again, over here, let's say the wave is traveling along the x-axis. This is your variation in the pressure. This is your pressure in excess, sometimes also called as excess pressure or variation, or just variation. Later on we'll draw another graph, don't worry about it. Sinusoidal wave equation of sound. That means the sound variations are also like a sine wave. So the graph looks something like this. What it means is, here the pressure is really high. That means the molecules are really close. So there is compression. Here also there is compression. That means the molecules are really close to each other. They are very dense. As you go away from this, the pressure will gradually reduce. Here it will become very less until it starts increasing over here again. That is how it should look like. Here the pressure is least, here the pressure is more. Again the pressure will start to decrease over here. Again over here. it starts to reduce. That's how it should look like. So compression, rarefaction, compression, rarefaction. That is how it looks like. Is this clear, my dear warriors? How the wave of sound is looking and how the graphical representation is? Because you can't see a graph or something going up and down for vibrations of air molecules. So that's why I have shown it graphically. This is a variation of the pressure from your normal pressure. So same thing, whatever I wrote before over here, I can write it. But instead of Y and A, what should I get? Think like this. I have given you something before. Instead of amplitude, what you should get is the pressure amplitude, maximum variation in the pressure. So what you will now get is change in the pressure is the pressure amplitude. You can write it as sine or basically cos, again doesn't matter. Okay, kx you can write first, or omega t you can write first, up to you, kx plus minus omega t. So this is how the equation looks like. What is PM? PM is basically this. This is basically your PM. This is your PM, which is your pressure amplitude, which I have already defined before. Pressure amplitude. Pressure amplitude. Now please remember, this is the variation of the pressure, but if there was no sound, then this yellow line would have been just a flat curve. That means it will be the same as the atmospheric pressure around me. So if I draw a graph of just pressure versus x, then mind it, there will be a small change. This will be the atmospheric pressure, and usually it is very huge, like 10 to the power 5 pascals, right? But the variations in the pressure, they are not in 10 to the power 5 or 3 or 2 or 1 also. They are in milli or micropascals. Yes, you heard me right. They are extremely small. So when I show this wave on an absolute pressure graph, you will see that the same graph might actually become something like this. Look at it. This is highly exaggerated. Not to scale, guys. So this is how it is. So you can see this one then becomes your pressure amplitude. What is that white dotted line? That becomes your atmospheric pressure. Is this absolutely clear now? How the variations are? Usually the pressure variations are very, very small, and also remember, they are so small that you can still detect it because our ears are sensitive. So this is actual pressure, which will be atmospheric pressure plus those variations which are happening right over here. Clear, everyone? Awesome, awesome. So this is sinusoidal sound wave equation. Perfect. Now, having said this, and phase difference, and in general the wave equation, okay, this is also done. I think we are good to go and solve some questions on this now. Here is the question. The excess pressure of a sound wave is given by 20 cos 4 pi x minus 100 pi t millipascal. Find pressure amplitude, wavelength, frequency, wave speed, direction of wave. Direction of the wave. These are the questions. Come on. Let's try to solve them one by one. I'll give you some time. You can also start trying it out on your own. It's not that difficult. This is some pressure equation. Very good. Disha, Krishna, Kaban, Sarvani, Dhanyu, Chandan, Evening Star. Yes, oxytocin. Everyone, come on, let's go. Just by direct comparison only, you can directly see that delta P is Pm instead of sine or cos, doesn't matter. And this is Kx and this is minus omega t. So direct comparison, you can get that the pressure amplitude is 20 millipascal, which is 20 into 10 to the power negative 3 Newton per meter square, whichever unit is given in the options. Next, direct comparison tells you K is nothing but 4 pi, which is nothing but 2 pi by lambda is nothing but 4 pi. Therefore, lambda is basically pi goes 0.5. So lambda wavelength is 0.5 meters. Next, direct comparison tells you 100 pi is omega and omega is 2 pi f. Therefore, 100 pi is 2 pi f. Therefore, frequency 2 pi goes, so 100 by 2 is basically 50 hertz. Wave speed is f into lambda. F is 0.5. This is 50. So 0 and point goes, 5 5s are 25. So 25 meters per second is the wave speed. Got it, everyone? No problem, Vismita. I'm so glad you guys are finally putting up your names in the chats or at least in the comments. Even if you are watching it recorded, at least I'll get to know you and know you by your names, because you guys are going to stay with me for a long time and we have to crack NEET together. NEET 2025 is our common objective, common goal. And when I see your photo in the newspaper or in the advertisement or maybe somewhere, I should know, okay, this is my student. So that's the reason why I keep asking you, always chat, always put a comment after the video ends. You should have that confidence. Yes, sir, I'm going to be our future doctor. All right. So this was this problem. We have done everything about it. Direction. Because it was negative. Negative means, what does it mean? It is going along the positive direction of x-axis. Positive direction of the x-axis. So that is the meaning of it. Perfect. Let's move to the next question coming up on your screen. Okay. Y is equal to A cos omega t plus or minus kx. Maximum particle speed is equal to 20 meters per second. Maximum particle displacement is 4 meters. Okay. Then wave speed is 100 meters per second. Question is, find along negative x. Question is, find the wave equation. Find the wave equation. That's the question. Some data points are given to you. From those data points, try to figure out which is the correct answer to this. All right. Come on, let's do this problem together, my dear students. Okay, let's try it out. Max particle speed is 20 meters per second. That means this is basically A omega. Max particle displacement is 4. That means this is basically A. Wave speed is 100. That means this is V. Okay. Now since amplitude is 4, A omega is 20. Since A omega is basically 20 and amplitude is 4, therefore omega will be nothing but 20 by 4, which is basically 5. So omega is 5. Okay, we have found omega. Wave speed, we all know, is nothing but omega by k, So K will be omega by V. Omega is 5. Wave speed is 100. So basically 100 by 5, that's 1 by 20. So K will be 1 by 20. So K we got, omega we got, A we got, plus or minus. It's going along negative x. That means there should be a positive sign. There should be a positive sign. This is going along negative x, so there should be a positive sign. So hence the correct answer of the wave equation will be y is equal to amplitude is nothing but 4. Cos is anyways there. Instead of omega, you will have 5t and positive sign over here. K will be 1 by 20. So x divided by 20. That's the wave equation. Is this fine, everyone? That's the wave equation. 4 cos 5t plus x by 20. Correct. Awesomeness. Let's move to the next question coming up on your screen. Here it is. Next question, guys, coming up on your screen. This is one of the best questions. Many students generally make a mistake in this particular question. Hopefully, you guys will not. Let's see. I'll mark some points. One, 2, 3, 4, 5, 6, 7, 8, 9. Okay. I've just marked few points. Question is, if the wave is going towards this side, question is, find the direction of the particles marked. Direction of the particles which have been marked at this instant. At this particular instant. So at the time shown, can you show me which direction is this going? It's a transverse wave. Very, very interesting question. Come on, let's see. Different particles have been marked. You have to figure out where are those particles moving at that particular instant. Are they going up? Are they going down? Are they going left? Are they going right? Are they not moving? Are they going at some other way? All right. Captain, I have some doubts. Can I ask you at the end of the class? Yes, sure, R. Vismita. No issues. Now, the trick to solve this problem, because a lot of you will think, sir, this is going up, sir, this is not moving, this is going down. I don't know how you will say that so easily. The best way to do that, and rather the only logical way to do that, is show the wave at the very next instant. At the very next instant. That means after some time. Because the wave is going here, right? So what will happen? This point, the crest will come slightly in the front, correct? The trough will come slightly in the front. So basically what would have been there here would have come here now. So the wave will probably look something like this. This is how it will look like. This is after delta t time, very small time. This is after some small time. Now it becomes obvious what each particle is doing. Observe carefully. Particle number 1 actually has come down. Particle number 2 has come to this position here. Particle number 3, it might feel like it has come down, but actually at that moment, it is at the extreme position. Particle number 3 is at the extreme position of the SHM. Just like this one over here. Extreme position, like this particle at now or now. So it is at the extreme position, correct? Even this particle might feel like it is moving, but actually right now this particle number 7 is at its extreme position, right? Then you can see particle number 4 has gone up. Okay, particle number 8 has definitely come down. Particle number 9 has definitely come down. Things which have gone up, particle number 4 has gone up, particle number 5 has gone up. This will be maximum speed actually, and this has also gone up. So basically particles 4, 5 and 6 are going upwards, whereas particle number 1, 2 and then 8 and 9, they are all going towards down, and particles labeled 3 and 7 are basically at rest. That is, the instantaneous velocity is 0. That is the answer. Got it? So lot of students make mistake, and you should see where is the wave going. Accordingly, draw the new wave after some time. If it was going towards the left, then you would have drawn it basically like this. Then all the answers will be exactly opposite except for 7 and 3, because they will anyways be at the extreme down or extreme up positions. That is how you solve this particular question. Okay, great. Now that we have seen what the wave equation, the wave parameters are, and everything over here. Sir, is there a way to actually find the wave speed without you giving it? Remember, you had told before that the wave speed actually depends on the inertial and elastic properties. The source decides the frequency. Yes, let's figure that out. What's that parameter which decides the wave speed? So, the wave speed on a string, the speed of a wave on a string is decided by two things. If you take a string and if you are generating some pulses, how much are you pulling it? So that pull is basically the tension in the string. Not just that, any part of that string, if you take that string element, that string might be like this. How much mass of the string is there per unit length, which is also called mu. Sometimes this mu can be also written down as density into area of cross section. Please remember, mu has the unit of kg per meter. This is kg per meter. You can also write it as density multiplied by area of cross section, area of that cross section, that is one and the same thing. So it depends on two parameters. How much mass is there per unit length? If you take 1 unit length of the string, how much mass is there and how much are you pulling it? These two parameters together decide the speed of the string, decides the speed of the wave on that particular string. And I can show that to you also very easily right over here. Check this out. All right, let's restart this. As you can see right now, the tension is very high. We can also have a timer maybe, but I don't need it. Okay, so let me start generating the pulse and see what exactly happens. Let me generate a pulse and see how fast it goes. So this is the pulse which was generated, and see it is going at this particular speed. Okay, it went out of the window. Okay, this had lot of tension. Let me make the tension small. The pull, the tension in the thread is small. See now what happens. The moment the tension becomes less, the speed also will become less, because it has very less elastic force. It is going very, very slowly, correct? But again, let me restart this, and yeah, let me get it back over here. Pulse, okay. Now if I put medium tension, you will see that it will probably go at a decent speed. Okay, now that was getting reflected, no issues. If I have very high tension, it will go really quick. If it has very low tension, it will go very, very slow. So tension definitely plays a very important role apart from how much mass is there per unit length. So the formula for that wave speed, the formula for that wave speed comes out to be root of the tension divided by mass per unit length. Mu is density into area of cross section, remember that. You can derive it easily, it is not that difficult. If you are thinking, sir, how did you get that? Exactly, see, density is mass divided by volume. Volume is nothing but area multiplied by length. So take that area on the top and you will have mass by length. So therefore, rho into A, mass per unit length, is nothing but mu. So that's how the derivation is, okay, for that. Okay. So anyways, this is a very important formula which you must know. Root of tension by mu. Root of tension by mu. This is for wave on a string. Similarly, sir, is there a formula for wave speed for sound? Wave speed of a sound wave? The answer for that is yes, definitely there is. But there are three different formulas depending on whether you are talking about solids, liquids or gases. Remember that. Number one, if you are talking about solid, I hope you know sound can travel in solids also. There were forts and palaces where the kings and the queens were able to hear what their ministers and other people in the town are talking about, because they had specially constructed walls through which the sound used to reach till their private chambers. So obviously sound can travel through wood, can travel through stone, marble. Yes, it might lose that energy very quickly if it is not a great material, but if you design it properly, use proper selection of materials, definitely the sound will travel till long distances. So in solids, it is root of, instead of tension, you have the Young's modulus, and instead of mu, you have just the density. If you notice, this tension mu, this tension, the pull and the mass per unit length, this is Young's modulus, this is density. This is exactly what I was talking about over here. Inertial and elastic property. Inertial property is mass per unit length, density. Elastic property is Young's modulus or the tension or the pull. So that is why both these things of the medium decides the wave speed, which is what I told you long time back. Okay, coming back over here. So this is for solid. But for liquid, when you are inside a liquid, then the speed of sound, instead of Young's modulus, you have the bulk modulus divided by density. So let me write down all these things over here. This is your Young's modulus. This is obviously your density. This is your bulk modulus. And this is obviously your density. Now there is a very interesting thing which happens for gases. For gas, when a similar analogy is used, the bulk modulus for a gas comes out to be the pressure. The bulk modulus comes out to be the pressure of that gas. This is the gas. If you assume that the compression and the rarefactions, if you assume that the compressions and the rarefactions are isothermal process, are isothermal in nature, which is exactly what Newton assumed. He found out that bulk modulus is the value of the pressure of the gas, and he got this derivation assuming it is an isothermal nature or process, because when there is a compression and rarefaction, he thought temperatures are not changing, so that is why he assumed that, and he got this answer. But unfortunately, this value, whatever you get, is incorrect. It is incorrect. And the reason why it is incorrect, it doesn't match practical values. It doesn't match practical values. These were okay. I mean, these formulas, whatever you derive using the formula and whatever you get practically, experimentally also, they were the same. So they were accepted, but this formula was not accepted. So then there was a guy called as Laplace. There was a guy called as Laplace. So there is something called as Laplace correction. Laplace correction. Now what is that Laplace correction? Laplace says that the process, he says that the compression and the rarefaction of sound is not isothermal, it is basically adiabatic in nature. Adiabatic in nature, since there is no time for heat exchange, no time for the heat to be exchanged with the surroundings or any such matter around it. So that's why when there is no heat absorbed or released, it becomes an adiabatic process. In such a situation, for that particular gas, you will see that instead of bulk modulus, I should put gamma P and that rho will stay as it is. Basically, the bulk modulus, I'll just write it down over here. Therefore, the bulk modulus becomes gamma times P. Now, you might be wondering what the hell is gamma? Well, gamma is nothing but that ratio Cp by Cv. You would have seen that 1.4, 1.66 for monodia, etc. And this P obviously is nothing but the pressure of the gas. The pressure of the gas. So that's it. So then the speed of the gas will then become root gamma P by rho. But P by rho, PM is equal to rho RT. So P by rho is nothing but RT by M. So you can also write this as root of gamma RT divided by molecular mass. This is also okay. Both the formulas are identical. It's just that what is constant, what is not constant, what is given decides things accordingly. Okay. So this T obviously is your temperature. R is your gas constant. M is your molecular weight. Molecular weight. Is that okay? So this is what you will use for gases, the Laplace correction, where he assumes the process to be adiabatic instead of it being a constant temperature, that is isothermal. That's the only correction which comes in gases. For solids and liquids, it's as it is. There is no problem in that. There is no problem in that. Thank you, Madhumati Mardai Krishna. Awesome. Great. So let's do some questions based out of this. Okay. So everything we have seen, the wave speed on a string, root T by mu, wave speed in solid, liquid and gases, everything has modulus on the top and masses or inertial properties at the bottom. So let's start. A string of mass 400 grams and 1000 meters has a tension of 100 Newton, on which an oscillator of 80 Hertz generates waves. Question is, find number 1 wave speed, number 2 wavelength. That's the question. Find the wave speed as well as the wavelength. A string of mass 400 grams and 1000 meters has a tension of 100 Newton. What's the wave speed? And the frequency is given. What's the wavelength? I think mass is given, length is given, tension is given. So wave speed was root of tension by mu, I told you. So tension by mu, mu is basically mass per unit length. So now start substituting everything. Tension is 100. Mass is 400 grams. So 400 into 10 to the power negative 3. Length is basically how much? 1000 meters. Okay. So 1000 will come over here. Okay. Let's see what exactly happens over here. Now these two zeros cancel. 10 to the power minus 3 goes on the top, will just become 10 to the power plus 6 divided by 4. This is 10 to the power 3. 10 to the power 3 divided by root of 4 is 2. So this is 1000. 1000 by 2 is nothing but 500. So 500 meters per second is our wave speed. Okay, 500 meters per second. Next step, finding the wavelength. V is nothing but f lambda. V is nothing but 500. Frequency is nothing but 80. So into basically lambda. Therefore, lambda will be 0, 0 cancels, 50 by 8. You can also write it as 25 by 4. You can also write it as 25 by 4 meter. That is the answer. Cool, everyone? Done, dusted? Perfect. Let's move to the next question. If a solid has a Young's modulus given by 2 into 10 to the power 11 Pascal and density of 8000 kg per meter cube, find the time taken by sound to travel 200 meters. Find the time taken by the sound to travel 200 meters in that particular solid. Young's modulus and density is given. From that, I think we can find speed. From speed, I think if distance is known, I can find the time taken also. So my first job should be to find the speed given by Young's modulus divided by density. Is that right? Okay. What's the Young's modulus? 2 into 10 to the power 11. What's the density? It's 8 into 10 to the power 3. Okay. So what happens? 11 and 3, it will become 10 to the power 8. This will just become 4. 10 to the power 8's root is 10 to the power 4. 4's root is 2. This is 10,000 by 2, which is basically 5,000 meters per second. That's really quick. We know that in solids, sounds actually travel faster in general. Once I know the speed, I can definitely find the time. Time is nothing but distance divided by your speed. Now the distance that you have to travel is just 200 meters. The speed with which you are traveling is 5,000 meters per second. So these two zeros will go. So you will be left with 2 by 50, which is just 1/25th of a second. If you want, you can also write it as 1000 divided by 25 milliseconds, right? So which is nothing but 40 milliseconds, which is basically 40 milliseconds. Yes, 40 milliseconds, correct. That is the answer to this. So that's how quick sound travels in solid. Awesomeness. In general, keep this in mind. That the speed of sound in solid is usually more than the speed of sound in a liquid, is usually more than the speed of sound in a gas. Like in air, example in air, the sound travels approximately at 340 meters per second. But in liquids like water, etc., I think the speed is around 1500 meters per second in water and all of that. In steel and all of that, it is in like, you know, tens and in metals, basically, in metals, it is like 5000 to 10,000 meters per second. So you can see the speed is usually huge in solid as compared to liquids, as compared to basically gases. So that's how different they are. Very good. Okay, great. This is also done. Next question coming up on your screen. This is one of the most famous question for string actually, where you have a string with some mass. The string itself has some mass and some length, and what you do is you are creating a small pulse over here. And that particular pulse will travel. The question is, how much time will it take? Will the pulse take to reach the top? To reach basically the top. That is the question. How much time will the pulse take to reach the top? Very interesting, guys. Now, in this type of question, you should realize that the problem is I can't just use velocity is root of t by mu. You will be like, sir, why sir we can't use? Because the problem is the tension is changing. Every point has a different value of tension, so I can't use this formula. Okay. So basically at every point the speed will be different. So because it's a rope with mass, the tension is not constant. The tension is obviously not constant, so even the speed is not a constant. Okay, so what I will do, I'll just take a random point here and I'll try to figure out what is the tension at this particular point. And maybe I will have to do some derivatives or integration. So at this point, if you ask me how much tension will be there, for that, think like this: whatever mass of the string is hanging over here, that should be pulled by the tension. So what is that weight of the string which hangs, which is hanging over here? That is exactly the value of the tension. So the weight of the string is the mass of the string which is hanging multiplied by g. How much mass is hanging? Well, this much length had a mass of m. This length m. This length how much? Simple. M by L multiplied by x. That's it. So this is exactly the tension. This much mass is how much for this much length? This length m. This length how much? Mass per unit length into x. Done, dusted. Clear? Oh, so the tension I have found. So I think we can now find the speed. So therefore the speed, which is variable, which is root of tension by mu, will be root of tension is mxg divided by L, mass per unit length m by L. So what will happen? LL cancels. I'll be left with root of xg. Okay, what to do now? You'll be like, sir, we have to do derivatives or integration. That's what normal teachers would have taught you here and there. But no, I don't think so we need it. Square both sides, so it will become v square is xg. Now deliberately I will add the term 0 plus xg. You'll be like, sir, why are you doing that? I'm getting an idea. 0, I can write it as 0 square plus, instead of xg, why not write it as 2 g by 2 into x. How does it make a difference? 2 will anyways cancel. This looks to me like our kinematic equation. V square is u square plus 2 acceleration into s. So basically the acceleration is g by 2, displacement is x, initial speed is 0, final velocity is v. Oh, so this is like kinematic equation, sir. Yes. So sir, what will you do next? Finding time. How do you find time? So now let's use s is equal to ut plus half at square. Okay. So what is my displacement, sir? Displacement is complete length of the string. So it is basically L. What is initial speed? 0. What is the acceleration? I got it as g by 2. What is the time? That's what I have to figure it out. So basically t square, therefore t square will be 2. So 4L divided by g. So therefore the time will be, 2 can be taken outside. So 2 root L by g. There is no pi over here because some of you will be like, sir, 2 pi root L by g, sir, simple pendulum. No. There is no pi here. 2 root L by g. That's the answer. Got it? Straightforward, everyone? Clear? So very, very nice problem which you are seeing over here. Next, let's go to the next question. If at room temperature the speed of sound is 300 meters per second, then what is the speed at (327 degree centigrade? What is the speed at 327 degree centigrade? Very interesting question. Now, clearly temperature is playing a role. So if you go back and see, speed of sound in gas by Laplace correction has a temperature formula also, gamma RT by m, whole thing under the root. So let's write it down first so that we get an idea of what has to be done. Just 1 second. Yeah. So if V is root gamma RT by m, if V is root gamma RT by m, obviously if temperature changes, velocity will change, and here you can see, therefore velocity is directly proportional to root of the temperature. But be careful, this temperature has to be absolute temperature. So when you talk about room temperature, what I'm saying is 27 degrees Celsius is nothing but 300 Kelvin. 327 degrees Celsius is nothing but 600 Kelvin. So therefore, by this logic, V2 by V1, which is root of T2 by T1, therefore V2 I don't know, initial speed is 300, correct? I think it is 300. T2 is 600 Kelvin, T1 is basically 300 Kelvin. Always temperatures in Kelvin. So V2 by 300, 600 by 300 is root 2. Therefore, V2 is 300 root 2 meters per second. That is the answer. Clear, everyone? Okay. So keep this in mind, how you will solve these models of questions. More models of questions. Let's come to that. More models of questions. Next question on your screen now. So this was with respect to temperature only, but imagine this is the question. The speed at 300 Kelvin, or let's say the speed at 400 Kelvin is 200 meters per second, what is the speed at 410 Kelvin? That is the question. So the temperature has been increased by 10 Kelvin. What do you think will the new speed be? That is the question. I'll be like, okay sir, it's the same thing like before. Yes, it is definitely the same thing like before. Velocity of sound is directly proportional to root of temperature. So the new speed by the old speed will be root of T2 by T1. So T2 is 410. This is 400. V2 by V1. V1 is nothing but 200. So therefore, V2 will be 200 multiplied by 0, 0 cancels, root of 41 by 40. 0, 0 cancels. But the problem is, in your options, you will not see this. In your options, you will see decimal values. Like, okay, sir, how do I calculate 41 by 40? Like, sir, 41 and 40 are close, so it is like 1. Root of 1 is 1, so 1 into 200 is 200. So answer will be 200. If you mark 200, then what's the point? Na? I mean, earlier speed was also 200. So it will be slightly more than 200. But then all the options will be more than 200. 201, 202, 203, 204. How will you find that out? So hence, now comes the application of binomial expansion and approximation, which you have learnt in basic maths. So what I will do this over here, V2 is nothing but, I will write it as 200. Instead of 41 by 40, I'll write it as 40 plus 1. 40 plus 1 divided by 40. The whole thing raised to half, which is then 200. 40 by 40 is 1 plus 1 by 40 whole raised to half. This is 1 plus x raised to n. Just check this out. This is 1 plus a small number raised to n is approximately 1 plus nx. That is your binomial approximation. Binomial approximation, if you remember. So exactly same thing we are using over here. So therefore V2 will be now not equal to approximately, that is what is required, 200, 1 plus n, n is basically half, into x, which is basically 40. So this is then 200 into 1 plus 1 by 80. That's it. So we can now easily calculate this. How much does it come out to be, guys? Come on, Madhumati, Disha, everyone. Calculate this. Everyone. Yes, thank you for all the fire, guys. Come on. 1 by 80, not that difficult. 1 by 8, 0.125. So it will be 0.0125. So 200 into 1 plus 0.0125, which is then 200 multiplied by 1.0125. So which will then be, what is the new speed? Come on, slightly more than 200, slightly more than 200. Come on, multiply it. How much will it come out to be? 0.1252 times. Come on, guys. 250. So this will be 202.5 meters per second. Just check this out. 202.5. Slightly more than 200, which is what we are expecting. So this is the catch in these kind of questions where you have to use binomial approximation. Binomial approximation. Cool. So we've done quite a few problems out here. Let's go to the last few things over here. Energy propagation in waves. See, whenever you talk about a wave which is traveling, right? This is the traveling wave direction. What it actually does is from the source towards the destination, from the source towards the destination, energy flows. Energy is flowing. Energy is flowing at a certain rate. Think about it over here. When I'm moving it up and down, my energy is slowly going here. It's going from one place to the other. If I don't move it, no energy goes. So the more I move it, the more energy will go from one place to the other. So whenever there is a wave, there is a energy flow which is happening from the source towards the final destination. Okay. But which kinds of energy go? Whenever this energy goes, it's of two forms. Like you can see, the particles are moving up and down. So what is there with them? Kinetic energy. Also the string, do you see it is getting elongated? Do you see the string is getting elongated? So there is elastic potential energy also. This energy flow which happens is basically, so the total energy of a wave, is of two forms. Number one, it is kinetic energy, and the remaining obviously is potential energy. Kinetic and potential both. But please keep in mind, the amount of kinetic energy in a wave is exactly equal to how much ever potential energy is there in a wave. How much ever potential energy is there in that wave. So if it has 10 joules of kinetic, it has 10 joules of potential, so total 20 joules of energy is going in that wave. So both energies are there in equal amounts. Both these energies are there basically in equal amounts. Very, very important. This also as well as this also. Till this point clear? Now there are two parameters that we define. One is called power of a wave, second is called intensity of a wave. Power of a wave, and the second is called intensity of a wave. When we say the power of a wave on, let's say, a string, it means how much energy is flowing per unit time. Usually this is associated with a string like this one. How much power is being consumed? 100 watt, 200 watt, 700 watt, usually with waves on a string. The second parameter, like I said, is something called as the intensity of a wave of sound. This is basically how much energy is flowing per unit time, per unit cross section. Basically, it is the power by area. So if you think carefully, you will realize the power is in watts. The power is always in watts. Basically, how many joules of energy is going per second, whereas intensity is expressed in watt per meter square, which is same as joule per second per meter square. How many joules of energy is going per second per meter square? This formula for a string comes out to be half mass per unit length wave speed omega square a square. Omega is angular frequency, A is amplitude. For sound waves, it comes out as half pressure amplitude square by density into velocity. PM square by rho v. That is it. Is that okay, everyone? So these are the two formulas which you should know, that how much energy goes per unit time, per unit area for sound when I talk is this much, half PM square by rho v, and this is half mu omega square A square, correct? That is what it is. Cool, everyone, till this point, clear? Yes. Come on guys, smash the like button. Yeah, everyone, I want to see everybody smashing that like button. Yes, thank you so much. Great, great. Okay, cool. Right. So this is also main topic which was done. Usually they don't ask questions from this, but still I have given this to you. Main thing that you should remember from here is basically be it intensity or be it power. Power is directly proportional to, or intensity is directly proportional to, always the square of the amplitude. Always the square of the amplitude. That is what the main thing that you should remember. Correct. All right. Okay. Cool. Now, one last thing before we close today's class. Whenever you reflect a wave, how does it behave? Reflecting a wave, how it behaves. If you take a string, generate a pulse, and make it reflect from a hard surface, you will see that when it comes back, the phase gets inverted. The phase is inverted, meaning the crest comes back as a trough. If it was a trough, it comes back as a crest. If this is a hard or basically a fixed end kind of a reflection. But if you take that same wave and make it reflect from something which is relatively free, then there is no phase inversion. A crest comes back as a crest, a trough will come back as a trough. So this is a relatively free or basically open kind of reflection. So there is no phase change. There is no phase change in these kind of reflections. Let's have a look at that as well. Let's look at this. Right now this is open. Whatever I generate is just going outside. Let me make the tension high so that it goes really quick. Let me make a fixed end. This is a fixed end. Let's see what happens. If I generate a pulse, see the crest comes back as a trough. Again trough, crest. Trough gets reflected, crest, trough, again fixed end. So this is what happens when you have a fixed end reflection. Let's make the tension slightly less so that it goes slowly. See this again. If I generate this, see how that crest goes as trough. Same thing, if I make a trough first, the trough will come back as a crest. Awesome, right? But if it is a loose end, that means it's like a ring which is attached to a rod which can slide freely. It's free to move. Oops, wait. If I make a crest, see what happens? It comes back as a crest. Here it will become a trough. The trough will come back again as a trough. It will become a crest because this is fixed. Again, it will come back as a crest. So no phase change. So that's how the waves reflect from a fixed or from a free end. Something very, very interesting again. Cool, guys. So these are the main things which are there in the waves part. Now interference, beats, organ pipes, standing waves, interference, all these things, I'll be doing it in a separate unit. Like I said, phasors and interference and combination of SHMs, all this has to be done together so that you get the true feel of it. That will be a separate class. But other than that, wave speed, intensity, energy, and these general things, they are done. These are the only things which are asked in the examination. Okay. So if you have loved this class, I want everybody to put up in the comment section, waved, okay, in the comment section. I want everybody to put this up in the comment section and make sure you're liking this video and as well as subscribing to the Vedantu NEET English channel. Okay. So I'll be letting you know when the next class will be very soon. Have a great time. Take care. Bye bye.